So we have here a typical view of Uranus as seen by a small telescope, an amateur astronomer view of Uranus. It's actually a pretty good picture for an amateur astronomer. Professional astronomers were not getting a whole lot better than that, particularly in the 70s and 80s. We really didn't know much about Uranus. So we needed to go and see it up close. And so in the previous lecture, I talked about how the Voyager 2 spacecraft was destined to be the first one to get there. It was launched in 1977, and so 9 years later, arrived in, or I guess 8.5 years later, arrived at Uranus. And so it finally gets there and gets us our first up-close view. Now, if you remember the lectures we've had so far this semester, the Voyagers, the first high-resolution images of the outer solar system. Pioneers 10 and 11 didn't really show very much detail. They were much lower resolution imaging systems. But the Voyagers, the first high-resolution imagers. And so they gave us our first up-close views. And so we had seen incredible detail at Jupiter, way beyond any telescope on Earth could see. They discovered that Jupiter had a ring. They saw the structures on Ganymede, suggestive of plate tectonics, smooth, billiard ball smooth, Europa with cracks on it, volcanoes on Io. This was like a startling sort of find. Amazing, shocking as how much detail, and things that we had never seen, wonders they just couldn't even hardly fathom. And then the spacecraft got to Saturn. Yeah, Saturn has these fantastic rings, but then they found the rings and all these ringlets. They found spokes in the rings. They found other sort of things. They found shepherd moons. They found co-orbital moons. They found moons that didn't seem to behave like other moons in the solar system. They realized that possibly Titan might have an entire weather system with methane. And so all these discoveries were this fantastic sort of thing. Unbelievable discoveries in here. So we'd seen all these worlds in such incredible detail. Everybody was excited to see what would Uranus look like up close. Because from far away, it's just a very small bluish-green dot. So up close, we got our first up-close views of it, and we saw a big bluish-green ball. Completely underwhelming. It was, all these other worlds had such dynamic weather systems, storms, clouds, cloud patterns, banding, stripes on them, all sorts of things they were expecting to see here, and they ended up not seeing that. They just saw a big featureless ball. Completely boring. Also completely odd, because as they were going past, they were able to measure the temperature, and they found the temperature was the same everywhere on the world, practically. Well, that was a little bit surprising, because after all, it's 21 years per season. So the South Pole was pointing at the sun for here. Well, actually, the South Pole had the sun shining on it directly for 82, or rather for 42 years, and the North Pole was in shade for 42 years. At this point, it was about half of that, but still, it was all about the same temperature, which means that something was circulating inside of this world, moving heat from one side to the other. That's a little odd, but not maybe horribly so. And all this methane out here was important. The color was due to methane. So this world was very, very rich in methane clouds. And methane is an even more potent greenhouse gas than carbon dioxide. So the methane was actually working to keep the heat in throughout the entire world. So that made this, made a little bit more sense. They found that Uranus did not give off more energy than it gets from the sun. Saturn did because of the helium rain releasing energy. Jupiter did because of Kelvin-Helmholtz contraction. This world gives all the same energy it gets from the sun. And they thought, well, that kind of makes sense. It's too small for Kelvin-Helmholtz contraction, too small for helium rain. Everything seemed to make sense that it's going to be less dynamic weather system because of its distance from the sun, less solar heating, less things that can generate internal heat. The interior structure, working this out took a long time. It was not immediately done after the Voyagers went by. They did a lot of work afterwards to figure out what was going on inside. And so one of the things they figured out was that the atmosphere is in fact hydrogen helium. As you get deeper inside of it, you do squeeze it to the point it becomes liquid hydrogen. Again, it's not an ocean of hydrogen because there's no distinct surface. It's going to be like on Jupiter and Saturn. It's above the critical point in terms of temperature and pressure. So at the top, it's just clearly going to be gas. At the bottom, it's clearly liquid. There's no dividing line between gas and liquid. It just gradually becomes one to the other. The core is a mixture of rock and metal. All these planetesimals that have rock and iron and so forth in them, they came together, they formed this world. Now, in the outer solar system, remember that you're going to have icy planetesimals. Things like Pluto are going to be what makes this up. So it's a mixture of rock and ice and metal. And so the heavier stuff sinks to the middle, making the solid core. All the other stuff, the water, forms a mantle around it. In the outer solar system, methane and ammonia are a big deal because these things are frozen. So ammonia salts in this mantle keep it a salty ocean. In fact, a big chunk of this world is water. Okay, so while it's considered a gas giant, it really should be definitely called a liquid giant. Okay, a water world. Okay, it has so much mass, its gravity is able to hold on to the hydrogen and helium, which are the most abundant things in the universe. But this is not really a gas giant in the same sense that Jupiter and Saturn are gas giants. This is a giant world that's got a solid core. It's mostly made of water, and above that is an atmosphere of hydrogen helium. It's liquid hydrogen near the bottom of that atmosphere, gaseous at the top. Now, I say there's water. That does not mean this is a place to go looking for life. It is under such extreme pressure that the water here is not going to behave in the same sense that you think of as water behaving. Yes, it is H2O, but it's going to behave wildly differently than anything that you're familiar with in terms of water. The pressure here is going to make it behave quite a bit differently. Okay, so just point it out. It is not really like an ocean as you would think of as ocean. The interior composition is about 14.5 Earth masses. The hydrogen and helium are believed to compose between 1/2 and 1.5 times the mass of the Earth. Well, notice that is a vastly smaller number than the total mass. So what makes up the rest of the mass? The rest of the mass is made up of the solid core and all these liquid ices. The liquid ices being liquid water, liquid methane, liquid ammonia, liquid carbon dioxide. This is where we don't really know. We think that the solid core might be as small as half the size of the Earth or as big as 3.5 times the mass of the Earth. I think most people think it's about 2 or 3 times the mass of the Earth, but we're not really sure. The rest of the difference between the solid core and the hydrogen and helium components are going to be those liquid ices. That makes up the bulk of this world. So, like I said, this should be called a water world or an ice world. Sometimes I've seen it referred to as an ice giant. Because obviously under the kind of pressures here that and temperatures, those ices would not be actual solids. Okay, but the thing that made it up, the icy planetesimals here, and so this is what we believe the interior composition is going to be. Now, there's a lot of question marks in here. If you look at that, up to this point, we've been fairly definite as to how much of something is going to be made of this or that. Here, these are huge uncertainties in here. So why so uncertain? It is because only one spacecraft ever visited this world, Voyager 2. Voyager 2 was launched in the 1970s. It was using, at best, early 1970 technology. They didn't want to put the latest and greatest technology into any spacecraft going this far because they weren't sure how it would actually behave in space. So they'd use tried and true technology. So probably about 1970 or 71 technology went into that spacecraft. That was not all that sophisticated, certainly by today's standards. And the spacecraft only flew by. It did not go into orbit, did not study it. It just flew past. So it was in the vicinity of Uranus really for a very short period of time. Just a couple days or so, just a few days in the vicinity making measurements. So there's a lot that it could not do. That spacecraft launched in the 1970s, arrived in 1986. 1986. That is before a lot of people in this class were born. Now, I was around, and I was actually at the time in graduate school when this went by, and so it was like, and I remember up to that point we had no idea what the interior of this world was like, and so this was a huge discovery, first up close views, but still, 86, no spacecraft has visited Uranus since 1986. That was the one and only spacecraft to Uranus or Neptune. Those two worlds are very poorly studied. In fact, we even know more about Pluto than we do about Uranus and Neptune because the New Horizons spacecraft was a vastly newer technology and far more capable than the Voyager spacecraft was. And so even though it flew by Pluto at the very edge of the solar system, very far from the sun, very low light, very poor measurements, that was better than we got about Uranus and Neptune. So most of what we know about Uranus and Neptune is still kind of speculative because we desperately need another spacecraft to go visit to study it up close.